So this is the Edexcel A-Level Maths 2023 Paper 3, and we're going to start with Part 1, Statistics. So for Edexcel, the third paper is the applied paper, and it's split up into two sections. So we've got the statistics first, and then we've got the mechanics. So, as I've said before, I teach AQA, and I know that there are a couple of sly little differences in the statistics for Edexcel. So obviously, namely is the large data set, which I am not well versed on for Edexcel. So when I inevitably get to the large data set question, I might have to refer to the mark scheme for that one, just because I haven't studied or taught with that document. So that's one thing. Another couple of things that I know Edexcel do that's slightly different to AQA. Edexcel includes linear interpolation, which is used to find the median or quartiles from grouped data. AQA don't do that. So there's a couple of little things, but overall they're identical. Okay, so let's crack on. So this is question number 1. The Venn diagram, where P and Q are probabilities, shows the 3 events A, B, and C and their associated probabilities. So part A, find the probability of A. So the probability of A is the 0.13 and the 0.25 added together. So 0.13 plus 0.25. And of course that's 0.38. Okay. So part B, the events B and C are independent. So if B and C are independent, that tells us that the intersection of B and C is equal to the product of the two probabilities. Okay, so we can use that because the intersection is 0.3. The probability of B will be 0.25 plus 0.05 plus the 0.3. So that's 0.25 plus 0.05 plus 0.3. And the probability of C is P and the 0.3. So P plus 0.3. Right, let's just erase those bits. Right, so we have 0.3 is equal to 0.25 plus 0.05 is 0.3 plus 0.3 is 0.6. So we have 0.3 divided by 0.6, and then take away 0.3 is 0.2. So that's P. And now we need to find Q. Well, Q is on the outside there, and will be 1 take away all of the other probabilities added together. Okay, so 0.13, 0.25, so Q is equal to 1 take away 0.13 plus 0.25. What else did we have? 0.05, 0.3. And P, which was 0.2. So 1 take away 0.13 plus 0.25 plus 0.05 plus 0.3 plus 0.2. And that's 0.07. Oh, whoops daisy. 0.07. There we go. Right. Part C, find the probability of A given not B. So the probability of A given not B is, using the formula for conditional probability, is equal to the probability of A intersection not B divided by the probability of not B. So we need to find the intersection of A and not B. So let's erase these bits first. Okay, so A is this, that's A, and not B is anything outside of B. So where do they intersect? Well, they clearly intersect here at 0.13. So that's 0.13. And the probability of not B, so if I get rid of those bits, the probability of not B is those three probabilities added together. So 0.13 plus P plus Q. So 0.13 plus P plus Q. So 0.13 over 0.13 plus 0.2 plus 0.07, and that gets us 0.325. And that's my answer. So this is question number 2. A machine fills packets with sweets, and 1/7 of the packets also contain a prize. The packets of sweets are placed in boxes before being delivered to shops. There are 40 packets of sweets in each box. The random variable t represents the number of packets of sweets that contain a prize in each box. State a condition, so part A, state a condition needed for t to be modelled by a binomial distribution with n as 40 and p as 1/7. Okay, so part A. So we could focus our attention on a couple of different things here. We could focus our attention on the probability being constant, or the events being independent, or talking about their being randomly selected. Okay, so I'm going to go with independence. It's always a good one to work through. And we need to make sure it's in context. Now, when you write down and explain independence, remember it's not that the probabilities are independent, it's that the events are independent. Okay? So, what I'm going to say is the event that a packet contains a prize is independent of another packet containing a prize. Okay, so I'm making sure that I'm writing it in context there. Okay, so part B, a box is selected at random. Using t is a binomial distribution with n is 40 and p is 1/7. Find, part 1, the probability that the box has exactly 6 packets containing a prize. So the probability of t being equal to 6. Okay, so different calculators do this in different ways, but you're going to want to go to your distributions and binomial distribution. Now, if you're on a class whiz, then you need to go to binomial PD, okay, because that's going to find you a particular value. I'm on the numworks here. So n is 40, p is 1/7, and we need x to be 6, or in this case t. So you should get a probability of 0.1727304, so 0.172724 decimal places. Okay, part 2. the probability that the box has fewer than 3 packets containing a prize. So fewer than 3 is the same as less than or equal to 2. So you can use binomial CD for this. So again, n is 40, p is 1/7, and we want less than or equal to 2. We should get 0.0616 to 4 decimal places. Okay, so Camille's sweet shop buys 5 boxes of these sweets. Part C, find the probability that exactly 2 of these boxes have fewer than 3 packets containing a prize. So now we've got a new binomial distribution. So X is a binomial distribution, let's call it X. And there are 5 boxes of the sweets. And we're looking at wanting to find the probability that exactly 2 of the 5 boxes have fewer than 3 packets containing a prize. So the probability that fewer than 3 packets contain a prize is the answer you got for B part 2. So that's the probability that's going in here. Now I'm going to use my full calculator display to make sure this is as accurate as possible. So 0.0615 8711. Now you should be able to get away with just using 0.0616. And we're looking for exactly 2. Okay, so 0.0615 8711, and we want exactly 2. So we should get 0.0313 to 4 decimal places. Okay. Camille claims that the proportion of packets containing a prize is less than 1/7. A random sample of 110 packets is taken and 9 packets contain a prize. Part D, use a suitable test to assess Camille's claim. You should state your hypothesis clearly. You should use a 5% level of significance. So we've got a binomial hypothesis test here. Okay, so let's go over to the next page. So part D. Let's start off with let P be the probability of a packet containing a prize. Okay, so we're looking at a probability of 1/7 here. So the null hypothesis is that P is 1/7. The alternative is that we're looking at less than 1/7. So we assume H0 is true, and we set up a binomial distribution for the packets. Now, there were 110 packets. So n is 110, and the probability is 1/7, and 9 were found to contain a prize. So we need to find the probability of x being less than or equal to, because it's got to follow the same direction as the alternative hypothesis, less than or equal to 9. So you want your binomial CD. N is 110, P is 1/7, and we want less than or equal to 9. So it's 0.0383 to 4 decimal places. And we need to compare that with 5%. So it's less than 0.05. So the result is significant. So we've got less than 0.05, so we reject the null hypothesis. If your p-value is less than the significance level, you reject. Result is significant, so we reject H0. And we can say there is sufficient evidence to suggest that, now, always check the wording here within the question. Camille claims that the proportion of packets containing a prize is less than 1/7. So there is sufficient evidence to suggest that the proportion of packets containing a prize is less than 1/7. So that's what I write down. So the proportion of packets containing a prize is less than 1/7. Okay, and we are done. This is question number 3. Ben is studying the daily total rainfall X millimetres in Leeming for 1987. He used all the data from the large data set and summarised the information in the following table. Part A, explain how the data will need to be cleaned before Ben can start to calculate statistics such as the mean and standard deviation. Okay, so in the table, final column, you've got trace, so TR. So we can't do any calculation until we've dealt with that. Okay, so the trace values in the large data set are values that are less than 0.05. Had to look that up. Okay, so for part A, we would need to replace TR, so trace, with a number. TR represents values less than 0.05. Okay, so it makes sense to replace TR with between 0 to 0.05. So we take the midpoint of that, so 0.025. So suggest replacing TR with 0.025. So that's midpoint of 0.05. Okay, so using all 184 of these values, Ben estimates the sum of x to be 390 and the sum of x squared to be 4,336. B. Calculate estimates for part 1, the mean daily total rainfall. So the mean is equal to the sum of x divided by how many there are. So 390 divided by 184, which is 2.11956. So 2.12. What's the units of this? Millimetres, I'm assuming. Millimetres. Millimetres to 3 fig. And the standard deviation is found using the sum of x squared over n, take away the sum of x over n all squared, or the mean squared, square rooted. Okay, so we've got 4,336 over n, take away 390 over 184 squared, square rooted. So let's put that in. 4,336 over 184 take away 390 over 184 squared, and that's 4.37 millimeters to 3 sig fig. Okay. So, part C. Ben suggests using the statistic calculated in part B1 to estimate the annual mean daily total rainfall in Leeming for 1987. Using your knowledge of the large data set, give a reason why these data would not be suitable. Okay, so had to look this one up as well. So the large data set for Edexcel, the data is from May to October, okay? And so what we're suggesting here is that we use the mean from May to October to represent the mean for the annual, the whole year, okay? Which seems a bit dubious because you're cutting out all the winter months, right? So the data only comes from May to October, and does not include well, November to April. Okay, so would not be a suitable sample. Okay, so part 2, state giving a reason how you would expect the estimate in part B1 to differ from the actual annual mean daily total rainfall in Leeming for 1987. Okay, well, if you're not including November to April, that's when you would expect the majority of the rain, right? Because that's your winter and spring months. So the consequence is that you would expect that the mean that we calculated previously would be lower than the total annual mean rainfall. So, part 2, as we are not including the winter spring months, we are ignoring when, or parts of the year, when the rainfall is likely at its highest. So we would expect that the total, the mean annual rainfall to be higher than the value calculated before. Okay, and that would be my answer. This is question number 4. A study was made of adult men from region A of a country. It was found that their heights were normally distributed with a mean of 175.4 centimetres and standard deviation 6.8 centimetres. Part A. Find the proportion of these men that are taller than 180 centimetres. So we have a normal distribution with a mean of 175.4 and a standard deviation of 6.8. So the variance is 6.8 squared. And we want to find the probability that x is greater than 180. So on your calculator, you want to go to normal CD if you're on a class whiz. I'm going to distributions, normal. You're going to want to put in 175.4 as the mean, standard deviation of 6.8. You want to put your lower in as 180 and the upper in as a large number. Okay, one here I'll just look at to the right, 180, and we should get 0.249371, so 2494 to 4 decimal places. A student claimed that the mean height of adult men from region B of this country was different from the mean height of adult men from region A. A random sample of 52 adult men from region B had a mean height of 177.2 centimetres. The student assumed that the standard deviation of heights of adult men was 6.8 centimetres, both for region A and region B. Part B. Use a suitable test to assess the student's claim. You should state your hypothesis clearly. You should use a 5% level of significance. So, first of all, let mu, so we're going to use a sample means hypothesis test here. Let mu be the population mean height of adult men from region B. So the null hypothesis would be that the mean is 175.4. The alternative, because we are looking at it was different, okay, so the claim is that it's different, then mu is not equal to 175.4. So we're looking at a two-tailed test. So assume H0 is true, and we set up a normal distribution for the sample means, which has a mean of 175.4 and a variance of 6.8 squared divided by the sample size, which is 52. So we're checking 177.2, which is to the right of the mean. So always go away from the mean here. So the probability of x bar being greater than 177.2. So we're putting the mean as 175.4. The standard deviation is the standard error now, which is 6.8 divided by the square root of 52. So on your calculator, you should have 0.9429903. And we're looking to the right. So lower as 177.2, upper as a large value. And we should get 0.0281 to 4 decimal places. Now we're going to compare that against the significance level, which is 5%, but because we're looking at a two-tailed test, we halve that, and so that is less than that's greater than. Dear oh dear. Fell at that hurdle. Greater than 0.025. Apologies. So, if it's greater than, the result is not significant, so we fail to reject. So result is not significant. So we fail to reject H0. So there is insufficient evidence to suggest that the population mean height of adult men from region B is different to the mean height of adult men from region A. Okay? Right, part C. Find the p-value for the test in part B. The p-value for the two-tailed test is twice the p-value that you got from your probability, right? So the 0.0281. So the p-value is equal to two lots of 0. So I'm going to use the full calculator display on this, 0.02814258. So 2 times 0.02814258 is 0.05628. So 0.0563 to 4 decimal places. And it's sometimes written as a percentage, so let's say 5.63%. To 3 significant figures on the percentage. So this is question number 5. Tissam is playing a game. She uses a ball, a cup, and a spinner. The random variable x represents the number the spinner lands on when it is spun. The probability distribution of x is given in the following table. Okay, where A, B, C, and D are probabilities. To play the game, the spinner is spun to obtain a value of x. Tissam then stands x centimetres from the cup and tries to throw the ball into the cup. The event S represents the event that Tissam successfully throws the ball into the cup. To model this game, Tissam assumes that the probability of S, given that x is equal to x, is k over x, where k is a constant. So what that's saying is the probability of Tissam successfully getting the ball into the cup, given that the distance from the cup is x, is k over x. So it depends, the success of her getting the ball into the cup depends on how far she is away from the cup. Okay? And she's suggesting the probability for that is k over x. We're also told the probability of S intersection x equals x should be the same whatever the value of x is obtained from the spinner. So the probability of S, so the probability of successfully getting the ball into the cup, and the probability of and the intersection of that with x is 20 or x is 50 or x is 80 or x is 100, these are all the same. Okay, using Tissam's model, part A, show that C is equal to 8/5 of B. Okay. This is quite complicated, this, isn't it? The notation is quite gnarly. Okay, well, let's first of all write down what we know about that notation, okay? So it's a conditional probability, so the probability of S, given that x is equal to x, is equal to the probability of S intersection x equals x divided by the probability of x being equal to x. Now, we're told that this numerator part is the same whatever value of x is obtained from the spinner. So you could rearrange this and then write the probability of S intersection x equals x is equal to the probability of S given that x is equal to x times the probability of x being equal to x. Now this still looks fairly complicated. What we're saying here is, because we're focusing on, because we'll look at C and B here, we'll look at these two for the moment. So when x is 50 and x is 80, we get B and C. So this part here is telling us that the probability of S intersection x equals, I've already forgotten what it was, 50. It says that that's the same, so that's equal to the probability of S intersection x equals 80. Okay, so given that this is equal to this times this, we can write the probability of S intersection x equals 50 as the probability of S intersection x equals 50, which is k over x. Now the x in this case is 50, so this is k over 50 times by the probability of x being equal to 50, which was B. And that's equal to, similarly for 80, so this bit where S intersection x equals x is k over 80 times by the probability of x being equal to 80, which is C. So the k's cancel away. We've got B over 50 is equal to C over 80. So if we multiply both sides by 80, we get C is equal to 80B over 5, or 80B over 50 rather, which is 8/5 of B, as required. Right. That's quite a lot to get your head around just for those 2 marks. So, part B, find the probability distribution of x. Now, that means we're going to have to find A, B, C, and D. Okay, so we've got C in terms of B. So, it would be a good idea if I could get C in terms of all the other variables, so A and D, because I know the A plus B plus C plus D has got to be equal to 1. So, I'm going to use the same methodology here to write C in terms of A and D. Now, the x value for A was 20. So, using the fact that the probability of S intersection x equals 20 will also be the same as the intersection with x is 80. We can say that k over 20 times A is equal to k over 80 times C. So if I divide through by k, multiply it by the 80, then C is going to be 4A. Okay? Now, if we use the same technique again, but this time for 100, then we get k over 100 times d is k over 80 times c. So c is equal to 80 over 100, which is 4/5 of d. Right. So, alongside c is 8/5 b, right, I now have c written in terms of a, b, and d, and I know that a plus b plus c plus d must be equal to 1. So a is 1/4 of c, b is 5/8 of c, c is just c, and d is 5/4 of c. So 1/4 plus 5/8 plus 1 plus 5/4 is 25/8. So c must be 8 over 25. Right. Okay, so x and the probability of x being equal to x. Now that we know c, we can find the others. So c is 8 over 25. So a is 1/4 of c. So 1/4 of 8 over 25 is 2 over 25. So a is 2 over 25. B is 5/8 of c. So that's 1/5. And D is 5/4 of C, which is 2/5. And that's my probability distribution. That was hard. That was hard. Okay, figuring out where everything came from and working with that notation. That wasn't easy. I'd definitely say that I haven't seen AQA do anything like that. Okay, Nav tries a large number of times to throw the ball into the cup from a distance of 100 centimetres. He successfully gets the ball in the cup 30% of the time. Part C, state giving a reason why Tissam's model of this game is not suitable to describe Nav playing the game for all values of x. Okay. So, what we're saying here then is the probability of S given that x is 100. So now it's getting it in 30% of the time, so that's 0.3. And that's got to be equal to, because we had k over x, didn't we? So yeah, using this formula here, that was k over x. So that's got to be k over 100. So that implies that k is 0.3 times 100, which is 30. So the question is, does that work for all other values? So let's check, shall we? Let's try it with If we tried it with the probability of S, given that X is 20, so if we start with that one and work our way through, if it's 30 over, well, X, isn't it? It's K over X. So you get 30 over 20, and that's greater than 1. So we've already found a reason why the model doesn't work. K can't be 30. So K cannot be equal to 30, as we have a probability greater than 1. So the model does not work for all values of X. Okay, so this is question number 6. A medical researcher is studying the number of hours T a patient stays in hospital following a particular operation. The histogram on the page opposite summarises the results for a random sample of 90 patients. Part A, use the histogram to estimate the probability of T being greater than 10 but less than 30. Right, let's go to the histogram. Here it is. So, part A, we're going from 10, so from there to 30. Okay, so probably makes sense to work out what each of the horizontal gaps are. So what's that, 10 to 15, and that's 10 little squares. So every 2 squares is 1. Okay, so the height of the first bit of the bar, so we're going to do this bit of the bar first, is 4.2. So probability of X being between 10 and 30 is equal to, so 4.2 times by 2, so that's the width, because we're going 4 blocks along, plus, so the next bit has a height of 4 and a width of 1, 2, 3, 4. Then our next block has a height of 3.5 and a width of 1, 2, 3, 4. And our final block has a height of 1 and a width of 10. And that's over the total number of patients, which was 90. Okay, so we have 4.2 times 2 plus 4 times 4 plus 3.5 times 4 plus 1 times 10 divided by 90, and that's 121 over 225, which is 0.5378. to 4 decimal places. Okay, let's have a look at the next bit. So for these 90 patients, the time spent in hospital following the operation had a mean of 14.9 hours, a standard deviation of 9.3 hours. Thomas suggests that T can be modelled by a normal distribution with a mean of 14.9 and a standard deviation of 9.3, or variance 9.3 squared. Part B, with reference to the histogram, state giving a reason whether or not Thomas's model could be suitable. Right. Here is the histogram. Okay. If we were to model it using a normal distribution, it would need to be symmetric, and this clearly is not. So the histogram is not symmetric. In fact, it's got positive skew. So a normal distribution would not be suitable. Okay. Chiang suggests that the frequency polygon based on this histogram could be modelled by a curve with equation y equals kx e to the minus x, where x is greater than or equal to 0 but less than or equal to 4, where x is measured in tens of hours, k is a constant. Part C, use algebraic integration to show that the integral between x e to the minus x between 0 and n, dx, is 1 take away n plus 1 e to the minus n. Well, I expect the students taking this paper didn't expect to have integration by parts appear in the statistics section. Okay, right. Right, fine. You can imagine that the examiner's having a bit of fun this day, won't you? Okay, so we need to integrate this. This is integration by parts. So the u is going to be x, dv by dx is e to the minus x, so du by dx is 1, and v is minus e to the minus x, integrating the dv by dx. So we go u times v, so that's going to be minus x e to the minus x, the value between 0 and n, take away the integral between 0 and n, of v du by dx. Now, we've got a minus sign there, so we're going to bring that minus sign out, make it a plus. Okay, so minus x e to the minus x, and then e to the minus x integrates to minus e to the minus x, so bring that into the square bracket. Right, substitute in the n, so minus n e to the minus n, take away e to the minus n. Substitute 0, we're going to get 0, take away e to the 0, so 1. So this gives us 1, take away n e to the minus n, take away e to the minus n. And we could factor e to the minus n out for the last two terms there, and have n plus 1 e to the minus n. Okay? And that's the answer we were looking for, so as required. Okay. Show that for Chiang's model, k equals 99 to the nearest integer. Okay. So we know that the total number of people staying in the hospital, so patients, was 90. So we need the area to be 90 when we integrate kx e to the minus x. And x is going between 0 and 4, so they're your limits on your integral. So for part D then, we are integrating between 0 and 4 of kx e to the minus x dx, and this has got to be 90. Now that k can come outside of the integral, as it's just a constant multiplier. So then we've got k times by, now I'm going to use this result here, 1 take away, now n here is 4, that's your upper limit of the integral, and that's going to be equal to 90. So k is 90 over 1 take away 5 e to the minus 4. So let's plug that in the calculator and see what we get. Hopefully we've got something close to 99. Yeah. So 99.0729. So approximately 99. Okay. Yeah, to the nearest integer. Okay. So E part 1. Estimate the probability of t being greater than 10 but less than 30 using Thomas's model of a normal distribution of 14.9 and 9.3 squared. So So 10 to 30. Okay, so on class quiz, you'd be going to normal CD. Put the lower in as 10, upper in as 30 for a normal distribution. 14.9, 9.3, 10, 30. And we should get 0.6486. Okay. And then part 2, what was part 2 saying? We've got to estimate it using Xiang's curve with equation y equals 99x e to the minus x and the answer to part C. Okay. So here we're going to be integrating. Now remember, it was in tens of hours, so we're not putting in 10 to 30 here, we're putting in 1 to 3 as the limits of the integral. 99 x e to the minus x dx. So that will be the integral from 0 to 3, take away the integral between 0 to 1. So that is 99 times by, so I just need to remind myself of the answer, which was this one again. 1 take away n plus 1 e to the minus n. So 1 take away n plus 1 e to the minus n. So e to the minus 3 there. And we're going to take away 99 times 1, take away, now the 0 to 1 bit, so n plus 1 e to the minus n. Okay? So we find this out. So 99, 1 take away 4 e to the minus 3, take away 99, 1 take away 2 e to the minus 1. And we get 53.12445, etc. Now remember, we need a probability here. So that's out of 90. Remember, that's the total area. And that gets us 0.59027, so 0.3 to 4 decimal places. Right. I think there was one last bit. Yeah, the researcher decides to use Xiang's curve to model the probability between A and B. So I guess that's without limit. State one limitation of Xiang's model. Well, Xiang's model only goes between 0 and 4. And remember, that represents 40 hours. So the model only goes up to 40, but if you want to go between any two times, then you can't use the model. So a limitation of Xiang's model is that it only works between 0 and 40 hours, but a patient may be there at the hospital for longer than 40 hours, and so the model doesn't work there. Okay, and so that's my answer to question number 6. So we've done the statistics section. We're now going to move on to the mechanics section. Now, there are again a couple of things that I know that Edexcel do in their mechanics section that's slightly different to AQA. Well, one main thing, I guess, and that's in the moments topic. So AQA doesn't look at any moments at angles, so it doesn't deal with ladder problems, for example, whereas Edexcel does. So that's really kind of the only key difference. So if you're, and that's not the only kind of like the board exam specification that is slightly different there, because OCR-A is similar to Edexcel and they do ladders, whereas OCR-B MEI does not. So if you are looking at this from an AQA, if you do AQA or you do OCR-B MEI, if we get to a moments question where it's at an angle, then you don't need that, whereas if you're doing Edexcel or you're doing OCR-A, then of course you do. So this is question number 1. A car is initially at rest on a straight horizontal road. The car then accelerates along the road with a constant acceleration of 3.2 meters per second. Find part A, the speed of the car after 5 seconds. So constant acceleration, so see that. So it's initially at rest, so U is 0. And we're accelerating at 3.2 meters per second. And for part A, we have t is equal to 5, and we want to work out the speed of the car, so v. So we're going to use v is equal to u plus at. So v is equal to 0 plus 3.2 times 5, and that's going to be 16, so 16 meters per second. So that is your speed. Right, part B. the distance travelled by the car in the first 5 seconds. So we're now interested in the distance. So we'll find the displacement. So we'll use S is equal to ut plus a half at squared, because that's the equation that doesn't have v. So S is equal to 0 times 5 plus 1 half times 3.2 times 5 squared. So 0.5 times 3.2 times 25 is 40. So 40 metres. So distance is 40 metres. And that's my answer to question 1. So this is question number 2. A particle P has mass 5 kilos. The particle is pulled along a rough horizontal plane by a horizontal force of magnitude 28 newtons. The only resistance to motion is a frictional force of magnitude F newtons as shown in figure 1. So part A. Find the magnitude of the normal reaction of the plane on P. Okay, so we're going to add to our diagram the weight, the weight acting vertically downwards, and which is going to be 5g, and then you've got the normal reaction working vertically upwards, which is r. So if we resolve upwards, then we have the normal reaction r, take away the weight, which is 5g, and that's going to be equal to 0 because we're not accelerating vertically. So r is 5g. Now Edexcel puts g as 9.8 unless otherwise stated. So 5 lots of 9.8 is equal to 49 newtons. Okay, so part B, the particle is accelerating along the plane at 1.4 meters per second. So accelerating at 1.4. So if we resolve, find the value of F. So if we resolve in the direction of motion, then we've got 28 working towards the right, so we've got the 28, and then we're going to take away the frictional force, and that's going to be equal to the mass times by the acceleration. So we'll have 28 take away 5 lots of 1.4, which is 21. So F is 21. The coefficient of friction between P and the plane is mu. Find the value of mu, giving your answer to 2 significant figures. So because the particle is moving, we have that F is equal to mu times r. So F we know is 21, and r we worked out as 49. So mu is 21 over 49, and we want to write that to 2 significant figures, which is 0.43. Okay, and that's question number 2. So this is question number 3. At time t seconds, where t is greater than or equal to 0, a particle P has velocity v meters per second, where v is t squared take away 3t plus 7i, plus 2t squared take away 3j. Find, part A, the speed of P at time t equals 0. So we need to substitute t is 0 into v. So that's going to give us 7i take away 3j. So all the t values go to 0. So the speed is equal to the length of that vector, which using Pythagoras is 7 squared plus negative 3 squared. So what's that? 49 plus 9, so 58. So square root of 58 meters per second. So 7.62 to 3 sig fig. Right. Don't forget your units. Part B, the value of t when p is moving parallel to I plus j. So if it's moving parallel to I plus j, so one along, one up, okay, then that would mean that its horizontal component would be equal to its vertical component. So in other words, the t squared minus 3t plus 7 would have to be equal to 2t squared take away 3. So if we move everything onto the right-hand side, subtract t squared from both sides, add 3t to both sides, take 7 from both sides. That's a quadratic we can factorise. So that's t plus 5, t minus 2. And so that's got two solutions, either t is minus 5 or t equals 2. So t must be equal to 2, as t cannot be equal to negative 5. We can't have a negative time. So t equals 2 is our solution. Part C, the acceleration of p at time t seconds. So when you're working with variable acceleration, think suvat, but ignoring u and t, right? So you've got displacement, velocity, acceleration, and you differentiate your way down and integrate your way up. Okay, so because you've got velocity and we want acceleration, we've got to differentiate our way down. So acceleration is dv by dt. So that's going to be 2t take away 3i, and then 4tj, and that's meters per second per second. So part D, the value of t when the direction of the acceleration of p is perpendicular to I. So I travels in that direction. So if it's perpendicular to I, okay, then that must mean that we don't want to be travelling horizontally, and so the 2t minus 3 has to be equal to 0. So the horizontal component of the acceleration has to be equal to 0. So t would be 3/2 or 1.5. Okay, and that's my answer to part D. So this is question number 4. In this question, I and j are horizontal unit vectors and position vectors are given relative to a fixed origin O. A particle P is moving on a smooth horizontal plane. The particle has constant acceleration, 2.4i plus j meters per second. So, suvat. At time t equals 0, P passes through the point A. At time t equals 5 seconds, P passes through the point B. The velocity of P as it passes through A is minus 16i minus 3j meters per second. Part A, find the speed of P as it passes through B. Okay, so part A. S, U, V, A, T. So, constant acceleration, 2.4i plus j. We're told the initial velocity because that is when it's passing through A, and that's minus 16i take away 3j. We want to find the speed of P as it passes through B. Now that happens at 5 seconds, so I want to find V. So V is equal to U plus AT is the suvat equation we want to use. So that's minus 16i minus 3j plus 2.4i plus j times t, which is 5. So we have minus 16 plus 2.4 times 5, so minus 4i. And then we've got minus 3, plus 5, so 2. So plus 2j. and that's meters per second. Now that's the velocity. We want to find the speed. So the speed is the length of that vector which is the square root of minus 4 squared plus 2 squared. So that's the square root of 20. So that's 2 root 5 meters per second, which is 4.47. to 3 sig fig. Okay. Right. The position vector of A is 44i take away 10j meters. At time t equals capital T seconds, where capital T is greater than 5, P passes through the point C. The position vector of C is 4i plus cj meters. Part B, find the value of T. Okay, so let's rewrite our suvat here. Because we're working at capital T here. The acceleration is 2.4i plus j, and the initial velocity is still minus 16i take away 3j. So now we'll talk about position vectors. We want to work with the displacement. So we want to work out that displacement. S is equal to ut plus a half at squared. So that's minus 16i take away 3j times capital T plus 1/2 times a, which is 2.4i plus j times t squared. So let's group everything together. The horizontal components first. So minus 16 times t, and then we've got a half times 2.4 times t squared, so plus 1.2 t squared, and that's I. And in the j direction, we're going to have minus 3 times t plus 1/2 times t squared j. Okay, so we know the position vector of A, and we know part of the position vector of C. So 44i take away 10j is where we're at A. If we add on the displacement vector, which we've just worked out, we will get to C. So in the horizontal direction, whoops daisy, in the horizontal direction, we will have 44, so that's from the 44i, so that bit there, plus the horizontal component that we've just worked out, which is minus 16t plus 1.2 t squared. So the horizontal component plus the horizontal component of the displacement must be equal to the horizontal component of C, which is 4. So 1.2 t squared take away 16t, take away 4 from both sides, gives us a quadratic in capital T. So let's solve that quadratic. So 1.2 x squared take away 16x plus 40. So we get 10 thirds, or 10. So t must be equal to 10. It can't be equal to 10 thirds because that's 3.3 recurring, and we know that t has to be greater than 5. So find the value of t, we've done that, t is equal to 10. Part C, find the value of C. So we'll use a similar method then, because we know the j component of A is minus 10, and we know the j component of the displacement vector that we found was minus 3t plus a half t squared. But we already know what t is, don't we? So we can substitute 10 into that, and that's going to be equal to c. So c is minus 10, take away 3 lots of 10, plus a half of 100, and that's 10. So c equals 10. This is question number 5. A small ball is projected with speed 28 meters per second from a point O on horizontal ground. After moving for t seconds, the ball passes through the point A. So that point there is when time is capital T. The point A is 40 meters horizontally and 20 meters vertically from the point O as shown in figure 2. The motion of the ball from O to A is modelled as that of a particle moving freely under gravity. Given that the ball is projected at an angle alpha to the ground, use the model to part A show that capital T is 10 over 7 cosine alpha. Okay, so I don't really have much space, so I'm going to have to go on to the other page. So for part A then, let's set up some suvat in the horizontal and vertical directions. Okay, so the horizontal acceleration is always 0, remember, and the vertical is minus g, so minus 9.8 in this case. So let's just quickly go back. We know that the initial velocity was 28, so we're going to split up that into its components, so 28 sine alpha for the vertical component and 28 cosine alpha for the horizontal. So 28 cosine alpha and 28 sine alpha. Okay, we've got those pieces. Right. Now we know that we reach point A after 40 meters horizontally and 20 meters vertically. So after 40 meters horizontally, we will get to point where the time is capital T. So we will consider the x direction, and we will use s equals ut plus a half at squared. So we've got 40 is equal to 28 cosine alpha times by t, which is capital T, plus a half at squared, which is 0 because a is 0. So t is 40 over 28 cosine alpha. 40 over 28 divided on 1 by 4 is 10 over 7. And that's what we wanted. So as required, 10 over 7 cosine alpha. Okay? So part B, show that tan squared alpha, take away 4 tan alpha plus 3 equals 0. Right, well, we're going to do a similar job then for the y direction. So again, using s is ut plus a half at squared. Sorry, not s. Look, we can use 20 now. So 20 is equal to u, which is 28 sine alpha, times by t, which is capital T, which we've just worked out, is 10 over 7 cosine alpha, plus a half times a, which is minus 9.8, times by t squared, so 10 over 7 cosine alpha squared. So we have 28 times 10, so 280, and then divide by 7. So 28 times by 10 divided by 7 is 40. So that's 40, and we've got sine over cosine there, so that'd be tan. So 40 tan alpha. Then we've got a half times minus 9.8 times by 10 over 7 squared, which is minus 10 over cosine squared. Now, 1 over cosine squared is sec squared. So we can write that like so. Now we can divide through by 10. Okay, and then of course we've got a trig identity that says that sec squared is tan squared plus 1. So 2 is 4 tan alpha, take away tan squared plus 1. So 2 is 4 tan alpha, take away tan squared, take away 1. So if we move everything onto the left-hand side, tan squared take away 4 tan alpha, then add 1 to both sides, and we get the quadratic as required. Okay, so that was the quadratic that we wanted to get. Part C, find the greatest possible height in meters of the ball above the ground as the ball moves from O to A. Right, the highest that it could be. Well, we need to know alpha, don't we? So we can solve that quadratic in tan because that factorizes. So that's tan alpha take away 3, tan alpha take away 1. So tan is 3, or tan is 1. Now of those two, tan alpha is 3 will give you the highest point because that's the steepest gradient. So remember that tan is opposite over adjacent. So if tan alpha is 3, then you're going 1 along, 3 up. Okay? So the hypotenuse will be 1 squared plus 3 squared, so 10 rooted, so root 10. So that means that we can use that right angle triangle. So that's definitely the one to use. Tan alpha being 1 will give you an angle of 45 degrees. So 1 along, 1 up. So 1 along, 3 up is a steeper angle, and so it's going to go up further. So I can use that because I can now write down sine alpha, which is opposite over hypotenuse, so 3 over root 10, and I can use that up here. Okay, so if we rewrite our vertical suvat, then I want to work out how far I go. The initial velocity was, 28 sine alpha. So 28 sine alpha, so 3 over root 10. So what's that? 28 times 3 over root 10. 42 root 10 over 5. The final velocity, because I've reached my maximum height, will be 0, and the acceleration was minus 9.8. So I want the suvat equation that doesn't have t, which is v squared is u squared plus 2as. So 0 is 42 root 10 over 5 squared plus 2 lots of minus 9.8 times s. So if I square that and then divide it by 2 lots of 9.8, we get s is 36. So 36 meters is the greatest height. Okay, right, there was one little bit more. The model does not include air resistance. State one other limitation of the model. Okay, well, remember we're modelling a small ball being projected. And we modelled that as a particle, which meant that you could ignore the spin of the particle. So, we modelled the ball as a particle, so we could ignore spin. This is another limitation of the model. So this is question number 6. A rod AB has mass m and length 2a. The rod has its end A on rough horizontal ground and its end B against a smooth vertical wall. So at A, we're going to have a normal reaction, so let's call that RA, and we're going to have a frictional force that's going to be acting to the right, okay, opposing the direction of motion because it's going to try and slip down the wall, and we'll call that friction at A. And B also is going to have a normal reaction force. Let's call that RB. Okay, the rod makes an angle theta with the ground, as shown in figure 3. Oh, by the way, there's no frictional force because it says for B, because remember it says it's against a smooth wall. The rod is at rest in limiting equilibrium. Part A, state the direction, left or right on figure 3 above, of the frictional force acting on the rod at A. Oh, I've already identified it's going towards the right. Okay, so how are we going to write that in words? Right, so part A, the rod is trying to slip down the wall or slide down the wall so the normal reaction at A is pushing to the left, so there's a normal reaction contact force that is pointing vertically upwards, okay? But what's happening is that it's pushing against the ground, so it's trying to push towards the left, so to your left, okay? And consequently friction must act to the right. And so friction must oppose this and work and act to the right. Okay, B. Where are we at? The magnitude of the normal reaction of the wall on the rod at B is S. Oh, I called it RB. Okay, let's call it S then. In an initial model, the rod is modelled as being uniform. Use this initial model to answer parts B, C, and D. Okay, so I was waiting to include this information on my diagram until I knew whether it was uniform or not. So now that I know it's uniform, I can put the centre of mass at the middle, and we can have the weight acting vertically downwards, which will be mg. Actually, let's move that. Have a little right angle triangle, mg, and so then we've got mg, and that's the opposite to the angle, so sine theta, and mg cosine theta as the adjacent side. Now, as for this one, this angle will also be theta, so the adjacent side is going to be s cosine theta, and the opposite side will be s sine theta. Unfortunate choice of lettering there. And we know that the rod has length of 2a, so it's a from A to the centre of mass. Right. So we want to take moments about point A. So, taking moments about point A will be 0. Total moments about 0. A will be 0. And we are A in distance away from the weight component. So, we're looking at this one here, okay? So that's the mg cosine theta, so we're A away from that. Now, that's going to be travelling around in a clockwise motion, and so that is negative. So we're going to have minus mg cosine theta. And then we're 2a away from the perpendicular component of this force. Now, I know that how I've drawn it, right, and where I've put my line, that doesn't look to be the whole distance along, right? This doesn't appear to be the whole distance. But that's not the point, because it's the actual force is acting at B, okay, the whole distance along. So, s sine theta, and that's going to be travelling around in an anti-clockwise motion. So, s sine theta, that would be positive. And that's going to be equal to 0. So we can divide through by A and rearrange this slightly and have 2s sine theta is equal to mg cosine theta. Then I could divide both sides by 2 sine theta, and I'll get s is mg cosine theta over 2 sine theta. And so you've got 1/2 mg cosine theta over sine theta is cot theta, as required. The coefficient of friction between the rod and the ground is mu. Given that tan of theta is 3/4, find the value of mu. Okay, so we know that because we're in limiting equilibrium, that F must be equal to mu times R. Okay, so let's write that down. So we need to think about resolving forces here. So let's resolve vertically first, taking upwards as positive. I need to keep going back between these two diagrams, between the diagram, don't I? So the normal reaction is travelling vertically. So we've got that one. We're going to be taking, so we've got R, take away mg, and that's it, right? They're the only forces that are acting vertically. So R take away mg is 0. So R equals mg. And we need to resolve horizontally as well. So horizontally, we have the frictional force and take away S. They're the only horizontal forces. So that means that the frictional force is equal to S, which we just worked out was half mg cot theta. So, we have been given in the question that tan theta is 3/4. So cot theta must be 4/3. So our friction is 1/2 mg times 4/3, and that's equal to mu times r, which is mg. So the mg's can cancel, and we've got the half times 4/3, meaning that mu must be 2/3. Okay. Part D. Find, in terms of m and g, the magnitude of the resultant force acting on the rod at A. So, we've got two forces at A. We've got the frictional force, and we've got the normal reaction force. So you can kind of think of that as a vector Fi plus Rj. So, we've got Fi plus Rj, and we want to find the magnitude of that. So we've got F, which was half mg cot theta with 4/3. So that's telling me that F is 2/3 mg. So we've got 2/3 mgi plus rj, which is mg j. So that's equal to the square root of 2/3 mg squared plus mg squared. So that's 4/9 plus 1, so that's 13/9 mg all squared, so m squared g squared, square rooted. So that's root 13 over 3 mg newtons. And so that's the resultant force. Okay, right. Last bit. In a new model, the rod is modelled as being non-uniform, with its centre of mass closer to B than it is to A. A new value for S is calculated using this new model with tan theta as 3/4, so the angle hasn't changed. State whether this new value for S is larger, smaller, or equal to the value that S would take using the initial model. Give a reason for your answer. Okay, so let's take a look at the diagram. So we're non-uniform now, and the centre of mass is closer to B, so it's somewhere maybe here. So that means that the distance from A to the centre of mass has increased. So let's do the calculation, right? Let's go back to what we did at part B, and we took moments about point A. Now, let's say that the distance from A to the new centre of mass is B, where B is greater than A. So B times minus mg cosine theta plus 2a times s sine theta is 0. So if you go through the same process as we did, with a bit of rearranging, we're going to get that s is b over 2a mg cot theta, yeah, mg cot theta. Now if b's greater than a, then b over 2a must be greater than half. Right? So comparing this with this, clearly s has increased. So s would be larger. So let's just go back to the question, just to make sure we're answering it correctly. Say whether this new value for s would be larger, smaller, or equal to the value that s would take using the initial model. Okay. So s would be larger as, well, the reason is for this, isn't it? This bit is larger here. So when we calculated the moment from A to the weight, so S would be larger as the moment of the weight of the rod about A would be larger. Yeah, okay, so that is question number 6.